The ultraviolet catastrophe. Before the year 1900, the universe seemed almost finished. Scientists believed they had found every rule that mattered. Gravity was understood, light was understood, heat was understood. The universe, they thought, was a machine with no more secrets left to find. But there was one tiny problem, one small glowing flaw in the math, and that flaw was about to tear the entire machine apart. Picture something simple: a hot piece of metal glowing orange in a fire, or a star burning quietly in the dark. Every warm object in the universe gives off light. This is just how heat works. Scientists had a beautiful equation to describe this glow, built from the laws of classical physics. The equation worked perfectly for red light, for orange light, for the warm colors you can see with your own eyes. But then they pushed the math further, into the shorter wavelengths, into the blues, the violets, and beyond, into ultraviolet light. The equation broke completely. It predicted that any warm object, even your own body right now, should be screaming out an infinite, endless amount of energy. Not a lot of energy. Infinite. A number with no end. This made no sense. If it were true, every fireplace, every star, every flicker of warmth in the universe would instantly release more energy than exists in all of creation combined. The room you are lying in right now would not exist. You would not exist. And yet here you are, warm, breathing, perfectly fine. The math said the universe should be impossible. Reality disagreed. This is the strange place where physics quietly broke. Not with an explosion, not with a bang, but with a single, embarrassing infinity sitting inside an equation that was supposed to describe something as ordinary as warmth. Scientists called it the ultraviolet catastrophe, because it felt like a crime against the universe itself. A tiny crack, hidden deep inside the laws of nature. The closer you looked, the wider it became. And somewhere in that crack, unnoticed at first, was a doorway. A door that did not lead deeper into the world we already knew. It led somewhere else entirely. Somewhere smaller, stranger, and far less certain than anyone had imagined the universe could be. Max Planck and the accidental birth of the quantum. In the year 1900, in Berlin, there was a quiet, conservative physicist named Max Planck. He was not a rebel. He did not want to break physics. He loved the old laws, the ones that had worked for centuries, and he believed in them deeply. All he wanted to do was patch the one small hole in the equation. The ultraviolet catastrophe. The embarrassing infinity. He thought it would take a clever trick, a small adjustment, nothing more. So he tried something strange, something he himself did not fully believe. He imagined that energy was not smooth and continuous, like water flowing from a tap. He imagined that energy came in small, separate packets, like coins instead of liquid, tiny, indivisible units. He had no proof this was true. It was simply a mathematical trick, a way to force the equation to behave. He called these small units quanta, from the Latin word for how much. He plugged this idea into his equation, expecting it to fail like everything else. It did not fail. The infinity disappeared. The numbers matched perfectly with what was actually observed in glowing objects. The catastrophe was solved. But solving it created a much bigger problem than the one it fixed. Because if energy truly came in these small, separate packets, then the universe itself was not smooth. It was not continuous, like a calm, flowing river. It was made of tiny, discrete steps, like a staircase. And nature does not build staircases by accident. Planck himself was deeply uncomfortable with this. He spent years trying to explain it away, hoping it was just a useful mathematical shortcut and not something real. He once admitted that his idea felt almost like a desperate act, a kind of placeholder, a trick to keep the universe from breaking. He did not yet realize what he had truly discovered. Think about what this means for everything around you right now. The dim light in your room, the warmth on your skin, the quiet hum of electricity in the walls. None of it is flowing smoothly. It is arriving in small, separate steps you can never directly feel, hidden just beneath the surface of every ordinary moment. Planck had not just fixed an equation. He had accidentally opened a door that led into a hidden layer of reality, one made of tiny, indivisible steps, a staircase built into the universe itself, and once that door was open, there was no way left to close it again. Einstein and the photoelectric effect. 5 years after Planck stumbled onto his strange staircase of energy, a young patent clerk in Switzerland was about to take that idea and make it terrifyingly real. His name was Albert Einstein. He was 26 years old, unknown, working a quiet desk job, reviewing other people's inventions during the day while rewriting the laws of the universe in his spare time. There was a puzzle that had confused scientists for years. Shine light on certain metals, and something strange happens. Electrons jump off the surface, like tiny sparks leaping into the dark. This was called the photoelectric effect. By the old laws of physics, light was a wave, smooth and continuous, like ripples spreading across water. And if light truly was just a wave, then a brighter light should always knock electrons loose with more force. But that is not what happened. You could shine the brightest, most powerful red light you wanted, and nothing would happen. No electrons would jump at all. Yet a faint, dim beam of violet light, far weaker, would knock electrons loose instantly. Brightness did not matter. Color did. Einstein looked at this and thought of Planck's strange idea, the one Planck himself did not fully believe. What if light was not just a wave? What if light came in small, individual packets, just like Planck's quanta? Tiny bullets of energy, later called photons. Each color of light carried its own fixed amount of energy, locked inside it. Red light photons carried too little energy to knock an electron loose, no matter how many of them you fired. Violet light photons carried just enough, even if you only sent a few. It was never about brightness. It was about the size of each individual hit. This meant light was not simply a wave gently washing over the world. It was also a stream of countless tiny particles, striking matter one at a time, like an invisible hail of bullets, too small and too fast to ever see. Think about that the next time you glance toward a lamp, or feel sunlight settle on your skin. What feels like one smooth, gentle wave of warmth is actually a relentless storm of countless tiny impacts arriving every fraction of every second. You, lying here in the dark, are being struck by an invisible rain that never stops falling. Einstein had just shown the universe was hiding two faces inside the same beam of light. A wave and a particle, both true, both impossible, existing in the same place at the same time. And nature was not finished revealing how strange it truly was. The first Solvay Conference. In the autumn of 1911, in a quiet hotel in Brussels, something unprecedented happened. The richest, most powerful minds in physics were gathered into one single room, paid for and assembled by a wealthy Belgian industrialist named Ernest Solvay, who wanted to bring the greatest scientific minds of his time together to solve the deepest mysteries of matter and energy. He had no idea he was about to host the birth of a revolution. Around that table sat names that would echo through the next century. Max Planck, still uneasy about his own discovery. Albert Einstein, the youngest person in the room, already famous, already feared by some of the older scientists for how easily he broke their settled laws. Marie Curie, the only woman present, twice a Nobel laureate, sitting among men who did not always know what to make of her. Henri Poincaré, Ernest Rutherford. The greatest collection of scientific minds the world had ever assembled under one roof. The topic on the table was radiation, and the quanta, Planck's strange staircase of energy. The idea nobody could explain, but nobody could ignore. For days they argued, calculated, and quietly admitted to each other a deeply unsettling truth. The old physics, the laws that had explained the universe for centuries, no longer worked at the smallest scales of reality. Something was broken at the foundation of nature itself, and none of them yet understood what was hiding underneath. What makes this moment so heavy to imagine is the silence behind the brilliance. These were not arrogant men, certain of their genius. Many of them left that room more confused than when they arrived. Einstein himself admitted that the conference revealed how little they truly understood, how the universe seemed to be quietly mocking their best equations. Poincaré, brilliant as he was, would die within a year, never seeing where this strange path would lead. This is the moment to sit with for a while. A room full of the smartest people of their generation, gathered together, facing the same suffocating realization, that the universe was not the orderly machine they had spent their whole lives believing in, that beneath the smooth, visible surface of reality, there was something smaller, stranger, and far less obedient than they ever imagined. They did not know it yet, but they were standing at the edge of a hole that went far deeper than any of them could see. And one by one, over the coming years, each of them would be pulled down into it. Niels Bohr and the atom that shouldn't exist. There was a problem sitting quietly at the center of every atom, one that should have made matter itself impossible. By the early 1900s, scientists pictured the atom like a tiny solar system, a heavy nucleus sitting in the center, with electrons circling around it, just like planets circling the sun. It was a beautiful picture. It was also a complete disaster. According to the old laws of physics, an electron circling a nucleus should constantly lose energy, the same way a spinning top slowly winds down and topples over. As the electron lost energy, it would spiral inward, faster and faster, crashing into the nucleus in a fraction of a second. By every known law of classical physics, atoms should collapse instantly. Matter should not be stable. You should not exist. The chair beneath you, the air in the room, your own body lying there right now, none of it should be able to hold itself together for even a heartbeat. And yet somehow, atoms do not collapse. Matter sits quietly, stable, unbothered, for billions of years. In 1913, a young Danish physicist named Niels Bohr looked at this impossible contradiction and made a strange, almost reckless proposal. He suggested that electrons could not orbit at just any distance from the nucleus. They were only allowed to exist in certain fixed, specific orbits, like rungs on a ladder, with nothing in between. An electron could be on one rung or another rung, but never in the empty space separating them. It could leap from one rung to another in an instant, but it could never collapse downward smoothly. There was no in-between space for it to fall through. This idea had no real justification at the time. Bohr could not fully explain why nature would behave this way. He simply forced the mathematics to work by borrowing Planck's strange quantum staircase and applying it directly to the atom itself. And astonishingly, it worked. The numbers matched. The atom became stable, on paper, for the first time. Lying here now, every atom inside your body is holding itself together, using rules that should not make sense. Your electrons are not falling. They are frozen in place on rungs of a ladder nobody built, obeying a law nobody had explained, and resisting a collapse that classical physics still insists should be happening to you right now, in this very moment. Bohr had not solved the mystery of the atom. He had only described its strange behavior, sketching the shadow of something deeper still hiding underneath, something that would take years and several more broken minds to finally uncover. The Bohr model picture, for a moment, a single hydrogen atom. Just one proton at the center, one electron circling around it. It sounds simple. It is the simplest atom in the entire universe. And yet inside this single, tiny structure, Bohr found a hidden rulebook for all of existence. Bohr's model gave specific names to those rungs on the ladder he had imagined. He called them energy levels, or shells. The electron closest to the nucleus sat on the lowest rung, holding the least energy. Further rungs held more energy, stacked outward like rings around the nucleus, except these rings were not smooth, continuous paths. They were fixed, separate distances, with nothing real existing in the gaps between them. Here is where it becomes strange enough to keep you awake, if only for a moment longer. An electron could jump from a lower rung to a higher rung, but only if it absorbed an exact, specific amount of energy, no more, no less, like a coin that only fits one precise slot. And when an electron fell back down to a lower rung, it released that exact same precise amount of energy instantly as a tiny flash of light. Bohr used this idea to explain something scientists had been puzzled by for decades: the strange, specific colors of light given off by glowing hydrogen gas. Not a smooth rainbow, but a series of sharp, separate lines, each one corresponding to an electron falling a specific number of rungs down its invisible ladder. The numbers matched perfectly. For the first time, someone had used the quantum idea to predict something real, something you could measure with your own eyes in a laboratory. Bohr had taken Planck's strange, uncomfortable staircase and built an entire model of the atom on top of it. But there was something deeply unsettling hidden inside this success. The model worked beautifully for hydrogen, the simplest atom there is. The moment scientists tried to apply it to anything more complicated, anything with more than one electron, it began to fall apart. The rungs no longer lined up. The predictions no longer matched. Bohr had built a perfect ladder for the simplest possible case and almost nothing else. Think about that, lying here in the quiet dark. The very atom that makes up most of the universe, the one inside every star, every drop of water, every breath you take, was the only one simple enough for a human mind to almost fully describe. Everything heavier, everything more complex, including the atoms that make up your own body, still hid behind a wall Bohr's ladder could not climb. Somewhere beyond that wall, something far stranger than rungs and ladders was waiting to be found. Louis de Broglie. In 1924, in Paris, a young French aristocrat named Louis de Broglie sat with a question that nobody else had dared to ask seriously. Einstein had already shown that light, something everyone assumed was a wave, could also behave like a particle. De Broglie looked at this strange fact and turned it completely around. If a wave can act like a particle, he wondered, then why couldn't a particle also act like a wave? This was not a small question. This was an idea that threatened to dissolve the line between two things that had always seemed completely separate. Particles were solid, located things, like tiny billiard balls sitting in one place at one time. Waves were spread out, rippling things, like sound moving through air, existing in many places at once. For centuries, these were two different categories, with two different sets of rules. De Broglie suggested that every piece of matter, every electron, every proton, perhaps even you yourself, carries a hidden wave alongside it, a wave that determines where that particle is allowed to be. He wrote down the mathematics for this idea as part of his doctoral thesis. His professors were so unsettled by it that they did not know whether to accept it. The proposal felt too strange, too unproven, more like philosophy than physics. They sent his thesis to Einstein himself for a second opinion. Einstein read it and said quietly that de Broglie had lifted a corner of a great veil. Without that endorsement, de Broglie's strange idea might have been dismissed entirely. Just a few years later, scientists fired beams of electrons through thin crystals and watched something that should have been impossible if electrons were only solid particles. The electrons spread out and interfered with each other, the exact same way ripples on a pond interfere when they cross paths. Solid little particles of matter were behaving like waves, exactly as de Broglie had predicted. Sit with that for a moment. Every electron orbiting every atom inside your body right now is not simply a small object circling in space. It is also a wave, rippling outward, occupying a strange, blurred region instead of a single fixed point. Bohr's rigid little ladder of rungs began to look less like a staircase and more like the fixed points where a vibrating wave settles into place, like the still points on a guitar string when it hums a single note. De Broglie had shown that the universe does not force matter to choose between being a wave or a particle. Every piece of matter is quietly living as both at once, and nobody yet understood what such a thing was even supposed to mean. The double-slit experiment. Imagine a single wall with two narrow slits cut into it, side by side. Now imagine throwing tiny grains of sand at that wall, one at a time. Some grains pass through the left slit, some through the right, and they land on a screen behind it, forming two simple piles directly behind each opening. This is exactly what you would expect from solid little objects. Simple, predictable, nothing strange at all. Now replace the sand with electrons, fired one at a time, slowly, patiently, so that only one electron passes through at any given moment. There is no way for one electron to interact with another. Each one travels completely alone. Logic says you should still get two simple piles, one behind each slit. But that is not what happens. Instead, after enough electrons have passed through, a strange pattern appears on the screen. Not two piles, but many stripes, a rippling pattern of bands, exactly like what happens when two overlapping water waves interfere with each other, some places reinforcing into a peak, other places cancelling out into nothing at all. This means each single, solitary electron somehow passed through both slits at once, not split in half, not divided. Each whole electron behaved as though it were a wave, spreading out, slipping through both openings simultaneously and interfering with itself, before landing as one single point on the screen, one electron, behaving as one wave, then collapsing back into one particle every single time. Here is where it becomes almost unbearable to sit with. If you place a detector beside the slits, just to peek, just to see which slit the electron actually goes through, the strange wave pattern instantly disappears. The electron stops behaving like a wave. It picks one slit, like an ordinary little object, and the two simple piles return, exactly as common sense would expect. The simple act of watching changes what the electron does. Not touching it, not disturbing it with force, simply observing it. Lying here now, in the dark, every electron inside every atom in your body is constantly making this same impossible choice, slipping between many possibilities at once, until something, somewhere, forces it to settle into one single, definite reality. Nobody has ever fully explained why looking changes anything. Scientists built entire careers, entire philosophies, entire decades of argument on this one unbearable mystery. A locked door hiding behind two narrow slits that no one has ever truly managed to open. Werner Heisenberg and the uncertainty principle. In 1925, a young German physicist named Werner Heisenberg retreated to a small remote island called Helgoland, suffering from a severe attack of hay fever, trying to escape the pollen of the mainland. Alone, with almost nothing else to do, he spent his nights wrestling with a question that had quietly haunted every scientist since the double-slit experiment first broke their certainty. If a particle behaves like a wave, spread out and blurred, then what does it actually mean to know where that particle is and where it is going? What Heisenberg found in the dead of night on that quiet island was something far stranger than a simple gap in measurement. He discovered a limit built directly into the fabric of reality itself. He found that you can never know both the exact position of a particle and its exact momentum, the direction and speed it is moving at the same time. Not because our instruments are too clumsy, not because we have not built a good enough microscope yet. The universe itself refuses to allow both pieces of information to exist clearly at once. The more precisely you pin down where something is, the more violently uncertain its motion becomes. The more precisely you measure how fast it is moving, the more its location dissolves into a blur. This was not a flaw in human knowledge. This was a flaw, or perhaps a feature, woven into existence itself. Heisenberg had discovered that reality, at its smallest scale, refuses to hold still long enough to be fully known. There is no hidden, perfect answer waiting underneath, just out of reach. There is no answer at all, not until something forces one to appear. Think about what this means for the world around you right now, in this quiet, dark room. Every electron inside every atom of your body does not have a fixed location and a fixed speed simultaneously. It exists instead in a strange, smeared cloud of possibility, a fog of where it might be and how it might be moving, with no sharper truth hiding beneath that fog, waiting to be discovered. Heisenberg's uncertainty was not really about uncertainty in our minds. It was about a deep, built-in fuzziness in the universe itself, a blur stitched directly into the foundation of matter. The closer you look at anything, the less solid it becomes, the less it resembles the firm, dependable world you believe you are lying in right now. And once this fuzziness was discovered, physicists could no longer pretend the universe was hiding a clean, exact answer somewhere underneath. There simply was no exact answer left to find. Matrix mechanics, That same night on Helgoland, before Heisenberg ever touched the question of uncertainty, he was already building something stranger underneath it, a new kind of mathematics, the kind that does not describe motion the way every other equation before it had ever described motion. He was trying to throw something away entirely. He wanted to stop imagining electrons traveling on neat, smooth little orbits, like tiny planets circling a tiny sun. He wanted to describe only what could actually be observed, not the imaginary path in between. Only the jumps. Only the flashes of light an electron gives off when it leaps from one energy level to another. What he built instead of orbits was a strange grid of numbers, arranged in rows and columns, where each number represented the probability of jumping from one specific energy level to another. Not a smooth path, not a story of where the electron travels in between. Just a table of jumps, a quiet ledger of possibilities, with no picture, no orbit, no familiar shape behind it at all. There was something deeply unsettling buried inside this new mathematics. When Heisenberg multiplied two of his strange tables together, he noticed the order mattered. Multiplying table A by table B gave a different answer than multiplying table B by table A. In ordinary arithmetic, the order of multiplication never matters. 3 times 5 is always the same as 5 times 3. But here, in this new quantum world, the order changed the outcome entirely. Heisenberg did not know it yet, but he had just rediscovered something mathematicians called matrices. Grids of numbers that do not always commute, that do not always behave the way ordinary numbers behave. This was not a small mathematical curiosity. This non-commuting behavior was the uncertainty principle itself, hiding quietly inside the multiplication, long before Heisenberg consciously understood what he was looking at. The order in which you measure position and momentum was already, secretly, changing the answer you would get, lying here now, somewhere deep inside every atom in your body. This same strange arithmetic is silently running, a grid of probabilities deciding which jumps are likely, which are rare, and which are impossible, with no smooth path connecting any of them, only sudden, ghostly leaps from one level to the next. Heisenberg had not found a new way to draw the atom. He had thrown drawing away entirely and replaced it with something closer to a hidden ledger of chance, one the universe consults silently, every fraction of every second, deciding what kind of jump comes next. Schrödinger and the wave equation. Heisenberg's strange grid of numbers unsettled almost everyone who saw it, including many physicists who agreed it worked, yet found it nearly impossible to actually picture. There were no orbits, no shapes, no pictures of any kind, just abstract tables of jumps and probabilities. Many scientists quietly admitted they could use the mathematics without ever understanding what it meant. This bothered an Austrian physicist named Schrödinger more than almost anyone else. In the winter of 1925, Schrödinger retreated to a quiet alpine villa, and there, drawing inspiration from de Broglie's strange idea that matter itself could behave like a wave, he built an entirely different kind of mathematics. Instead of Heisenberg's abstract grids of jumps, Schrödinger wrote a single, elegant equation describing a smooth, continuous wave, spreading through space and changing gently over time. He called it the wave function. Rather than tracking sudden leaps between fixed energy levels, his equation described something flowing and continuous, closer to ripples spreading across the surface of still water. When Schrödinger applied his wave equation to the hydrogen atom, something remarkable happened. The same energy levels Bohr had stumbled upon years earlier, those rigid little rungs on an invisible ladder emerged naturally from his smooth, flowing mathematics without forcing anything by hand, the wave equation produced the exact same answers as Heisenberg's strange grids of numbers, despite looking nothing alike. Two completely different forms of mathematics, one built from sudden jumps, one built from smooth, continuous waves, were somehow describing the exact same hidden reality. This left physicists with an uncomfortable, lingering question. What exactly was this wave a wave of? Schrödinger originally pictured something physical, an actual smearing of the electron itself, spread thin across space, like a charge slowly diffusing outward. But this picture, comforting as it was, would soon be challenged and reinterpreted in ways Schrödinger himself never fully accepted, in ways that would haunt him for the rest of his life. Right now, every electron inside every atom in your body can be described by one of these wave functions, an invisible flowing pattern, stretching gently through space, holding within it every possibility of where that electron might be found, before anything has been measured, before anything has been forced to settle into one single, definite place. Schrödinger had given quantum mechanics something it desperately needed, a single, beautiful, continuous mathematics that could be visualized, that did not depend on strange grids of unseen jumps. But the question of what that wave truly represented, what kind of reality it was actually describing, would soon pull him into a thought experiment so unsettling that his own name would become forever attached to a cat that was both alive and dead at the same time. Schrödinger's cat. By 1935, Schrödinger had grown deeply uneasy with where his own equation was being taken. Other physicists had begun to insist that his smooth, flowing wave did not represent a real physical smear of matter at all. Instead, they claimed it represented something far stranger, a wave of pure possibility, a fog of every outcome that could happen, all existing at once, until the moment someone looked. Schrödinger hated this idea. So he built a thought experiment, not to support it, but to expose how absurd he believed it truly was. Picture a sealed steel box. Inside it, a cat. Also inside the box, a small amount of radioactive material, so small that within 1 hour there is exactly a 50% chance that a single atom inside it will decay. Connected to this radioactive atom is a device, a hammer, poised above a small vial of poison gas. If the atom decays, the hammer falls, the vial shatters, and the cat dies. If the atom does not decay, nothing happens, and the cat lives. The box is completely sealed. No light, no sound, no way to peek inside. According to the strange new interpretation of quantum mechanics, before anyone opens that box, the radioactive atom exists in a blurred combination of both decayed and not decayed at the same time, and because the cat's fate is directly tied to that atom, logic demands that the cat itself must also exist in a blurred combination of both states. Not unconscious, not in some kind of coma, but truly, physically, both alive and dead simultaneously, smeared together in the same impossible cat, frozen until the moment the box is opened and reality is forced to choose. Schrödinger meant this as a kind of mockery, a way of showing how ridiculous it sounded to apply quantum blurring to something as large and solid as a cat. Surely, he thought, a cat cannot be both alive and dead. Surely there must be some hidden, deeper truth, some missing piece of the puzzle that quietly decides the cat's fate long before anyone opens that box. And yet, decades later, no missing piece has ever been found. Physicists still argue, even now, about what exactly happens inside that sealed box, about whether opening the lid creates reality or simply reveals something that was already quietly decided. Lying here, in your own sealed room, in the dark, you might wonder what tiny, invisible coin flips are happening around you right now, blurred and undecided, waiting only for something or someone to finally look. The Copenhagen interpretation. While Schrödinger was busy trying to embarrass the strange new quantum logic with his cat, Niels Bohr and Werner Heisenberg were busy doing the opposite. They were trying to build a framework solid enough to actually live inside that strangeness rather than run from it. Working together in Copenhagen through the late 1920s, they assembled an answer that would come to be called the Copenhagen interpretation, and it remains even now the closest thing quantum mechanics has to an official explanation. The idea at its center is almost too simple to feel comforting. Before a measurement happens, a particle does not have one fixed location, one fixed speed, one fixed anything. It exists only as a wave of pure possibility, a fog of every outcome it could become, all overlapping at once. This is not a question of hidden information we simply haven't found yet. According to Bohr and Heisenberg, there is no hidden information at all. The fog is the whole truth. Nothing is being concealed from us. Nothing is waiting underneath to be discovered. Then, the moment a measurement happens, the moment something interacts with that particle in a way that forces an answer, the fog collapses. Instantly, completely, without warning. One single outcome is chosen, at random, governed only by probability. And every other possibility the particle could have become simply vanishes, as though it had never existed at all. Bohr called this the act of measurement, and he refused to explain what physically causes the collapse, or what measurement even technically requires. He simply insisted that asking what happens underneath the fog before it collapses was a meaningless question. Not difficult, not unsolved, meaningless. This unsettled many physicists who heard it, including Einstein himself, who spent the rest of his life resisting it. A universe with no hidden answers, only random collapses appearing out of nowhere, felt less like physics and more like surrender. But Bohr held his ground, insisting that nature itself might simply refuse to be pinned down by the kind of certainty humans had always assumed it owed us, lying here now, in this quiet, dark room, somewhere inside your own body. Countless tiny fogs of possibility are being interacted with, collapsed, and resolved, every fraction of every second, without your awareness, without your permission, into outcomes that were never decided in advance, not hidden from you. Simply not real yet, until the universe, for reasons no one has ever fully explained, finally chooses one. Wolfgang Pauli and the exclusion principle. By the mid-1920s, physicists had a strange new puzzle on their hands. If electrons truly behaved like waves of possibility, spread out and blurred, then what was stopping every electron in an atom from simply collapsing down into the lowest possible energy level, all of them crowding together in the same exact spot, like water settling to the bottom of a container? Nothing in the mathematics so far seemed to forbid it. And yet, this is not what happens. Atoms build outward, layer by layer, electron after electron, stacking into distinct shells instead of collapsing into one single crowded point. In 1925, an Austrian physicist named Wolfgang Pauli found the hidden rule the universe was quietly obeying. He discovered that no two electrons in an atom can ever exist in the exact same quantum state at the same time, not crowded together, not stacked on top of one another. Each electron requires its own unique identity, its own distinct set of properties, and the moment one electron claims a particular state, every other electron in that atom is forbidden from ever occupying that exact same state again. Pauli called it the exclusion principle, and it would turn out to be one of the quietest, strangest laws ever written into the fabric of matter. This single rule is the reason atoms do not collapse into identical points. It is the reason elements stack into layers, building the entire structure of the periodic table, shell after shell, each one slightly further out than the last. Without this one rule, carbon would not behave like carbon. Oxygen would not behave like oxygen. Chemistry itself, the entire foundation of biology, the entire foundation of you, would simply not exist in any recognizable form. There is something almost unbearable in how quiet this law is. It does not announce itself. It does not glow or hum or pulse. It simply sits underneath everything, a silent boundary that every electron in the universe obeys without exception, without hesitation, without ever once being caught breaking it. Lying here now, every electron inside every atom of your body is occupying its own private, unrepeatable state, locked into place by a rule none of them can resist, a rule with no enforcer, no mechanism, no visible reason for existing at all. Just a quiet, absolute refusal, woven into the structure of reality, ensuring that no two electrons, anywhere, in any atom, in the entire universe, will ever be willing to share the exact same place at the exact same time. The Einstein-Bohr debates. By the late 1920s, two of the greatest minds of the century found themselves on opposite sides of a divide that would never fully close. Niels Bohr believed quantum mechanics, strange as it was, described the deepest truth about reality that anyone could ever reach. Albert Einstein could not accept this, not because he misunderstood the mathematics. He understood it perfectly. He simply refused to believe that the universe, at its core, was built on randomness and incompleteness. And so began one of the longest, most respectful, most relentless arguments in the history of science. Their battlefield was the Solvay conferences, the same gathering that had once brought the founders of quantum theory together in confusion nearly 2 decades earlier. Now, in 1927 and again in 1930, Einstein arrived each morning with a new thought experiment, carefully built to expose a flaw, a contradiction, some hidden crack in the strange new framework Bohr and Heisenberg had constructed. Each time, Bohr would spend the day pale, anxious, sometimes barely sleeping, until by evening he had found a way to dissolve Einstein's challenge, often by reaching even deeper into the same strange logic Einstein was trying to defeat. One of Einstein's most famous attempts involved an imaginary box filled with light, designed to measure energy and time with a precision quantum mechanics insisted was forbidden. For one tense night, it seemed Einstein might have finally broken the uncertainty principle itself. By morning, Bohr realized the answer, and it was almost cruelly elegant. Einstein's own theory of gravity, the very theory that made him famous, was the missing piece that saved Heisenberg's principle. The box, sitting in a gravitational field, would shift time itself by just enough to restore the very uncertainty Einstein was trying to escape. Einstein had unknowingly used his own genius to defeat himself. These were not bitter men, attacking one another out of spite. They respected each other deeply, even as neither one ever truly surrendered. Einstein later admitted that no one had shaken his convictions about physics as deeply as Bohr had, while Bohr would describe Einstein's relentless challenges as some of the most important contributions to refining the very theory Einstein refused to fully accept. Lying here now, you are witnessing the quiet aftershock of that disagreement, one that never fully resolved. Decades after both men have gone, physicists are still divided over the same fundamental question that once kept them arguing late into the Belgian nights, whether the universe holds a hidden, deeper order waiting patiently to be found, or whether the randomness Bohr defended truly is the final, unyielding face of reality itself. Einstein's "God does not play dice with the universe." Among all the lines exchanged during those long, exhausting debates with Bohr, one phrase from Einstein has outlived every equation, every thought experiment, every late-night argument in Brussels. He said simply that he could not believe God plays dice with the universe. It sounds almost gentle, almost poetic. Underneath it was the deepest fear of his entire scientific life. Einstein was not arguing about religion. He used the word God the way a poet uses a word for something vast and orderly, not a being with a face, but a deep structure of law and reason holding the universe together. His entire career had been built on the conviction that reality, no matter how strange it appeared, must ultimately obey clean, determined rules. Effects must have causes. Nothing should happen without a reason hidden somewhere beneath it. The universe, to Einstein, was not allowed to simply shrug and roll a die. Quantum mechanics, as Bohr and Heisenberg described it, demanded exactly that. A radioactive atom does not decay for a reason. It simply decays at a random moment, governed only by probability, with no hidden cause waiting to be uncovered. An electron does not choose its position because of some deeper, secret variable. It has no position at all until measurement forces one to appear, chosen by pure chance. To Einstein, this did not look like a discovery. It looked like physics quietly giving up, mistaking its own ignorance for a fundamental law of nature. Bohr's reply to him has also outlived its moment. He gently suggested that Einstein should stop telling God what to do. It was not mockery. It was a quiet admission that even the universe's deepest laws might not owe us the comfort of certainty. What makes this argument so heavy, even now, is that history has not fully sided with either man. The randomness Einstein hated has been tested again and again, and every test has sided with Bohr. And yet the deeper question Einstein was truly asking, whether something is hiding beneath that randomness, has never been completely closed. Lying here, in this quiet dark, somewhere inside your own body, atoms are deciding things at random, with no cause, no hidden reason, no die actually being rolled, and yet behaving exactly as if one had been. Einstein spent the rest of his life unable to accept that this could be the final truth of reality. He never found the dice. He only ever proved again and again just how well they were hidden. The EPR paradox. In 1935, Einstein made one final, desperate attempt to prove that quantum mechanics was hiding something incomplete. Working with two younger physicists, Boris Podolsky and Nathan Rosen, he published a paper designed not to disprove quantum mechanics, but to expose what he believed was a deep crack running underneath it. They called it, simply, a description of a paradox. History would shorten it to 3 letters, the initials of its 3 authors, the EPR paradox. Picture 2 particles created together in a single shared event, then sent flying apart from each other in opposite directions until they are separated by enormous distances, even light years apart. According to quantum mechanics, these two particles remain connected, linked by a single shared wave function, even after they are far apart. Measure one particle and force it to settle into a definite state, and the other particle, no matter how far away, instantly settles into a matching, correlated state as well. Instantly. Not after a delay. Not limited by the speed of light. Instantly. Einstein found this unbearable. His own theory of relativity insisted that nothing, no signal, no information, no influence of any kind, could travel faster than light. And yet here was quantum mechanics, quietly suggesting that measuring one particle could instantaneously affect another, sitting calmly on the opposite side of the universe. Einstein refused to believe this meant some strange, invisible influence was leaping across the void in an instant. He called it, with open scorn, spooky action at a distance, and insisted that the only sane explanation was that both particles must have been carrying some kind of hidden, secret instructions all along, fixed at the moment they were created, simply waiting to be revealed later, like two sealed envelopes carrying matching answers, written long before anyone opened them. To Einstein, this was the final proof that quantum mechanics was incomplete. Something deeper, some hidden variable, some secret layer of reality, had to be quietly filling in the gaps that randomness alone could not explain. He was certain, given enough time, someone would find it. Lying here now, somewhere in laboratories around the world, particles separated by vast distances continue to mirror each other's fate the instant either one is measured. A quiet, invisible thread stretching across space, refusing to be explained away as mere coincidence. Einstein died still believing those hidden envelopes existed somewhere, still sealed, still waiting. He never lived to see the experiment that would finally test whether his sealed envelopes were real, or whether the universe truly was as spooky and as connected as he feared. Paul Dirac and the equation that predicted antimatter. In 1928, a quiet, famously withdrawn English physicist named Paul Dirac sat down to solve a problem that had nothing to do with paradoxes or arguments about dice. He was simply trying to fix a technical flaw. Schrödinger's beautiful wave equation worked well, but it had not been built to fully respect Einstein's theory of relativity. It worked for slow particles, but began to break down for electrons, moving at speeds close to the speed of light. Dirac wanted a wave equation that could finally satisfy both quantum mechanics and relativity at the same time. What he found instead was something far stranger than a simple repair. When Dirac solved his new equation, it gave him two answers for every electron. Not one. One solution described an ordinary electron with positive energy, behaving exactly as expected. But the mathematics insisted on a second solution as well, one with negative energy, a kind of mirror version of the electron that nothing in the known universe had ever observed. Most equations in physics quietly produce extra, meaningless solutions that scientists simply discard, treating them as mathematical noise rather than physical reality. Dirac refused to throw his second answer away. Instead, he made an extraordinary leap. He proposed that this second solution was not nonsense at all. It was a real particle, nearly identical to the electron in every way, except for one crucial difference. Where the electron carried a negative charge, this new particle would carry a positive one, a perfect mirror image of ordinary matter. He called it, almost reluctantly, antimatter, a substance the universe had never been observed to contain, predicted purely from the stubborn insistence of an equation that refused to be simplified. Just 4 years later, in 1932, a young American physicist named Carl Anderson, studying cosmic rays raining down from space, found a strange particle track curving in exactly the wrong direction inside his detector, a particle identical to the electron in every way, except for its charge. Dirac's imaginary mirror particle was real. They named it the positron, and antimatter stepped out of pure mathematics into physical reality. Lying here now, somewhere above you, cosmic rays from deep space are still occasionally creating tiny flashes of antimatter, fleeting mirror particles that exist for only a fraction of a second before annihilating themselves the instant they touch ordinary matter. Dirac had not gone looking for a mirror universe of matter. He had simply refused to throw away an answer his equation insisted was real, and in doing so, he proved that sometimes the strangest, most unbelievable consequences of mathematics are not mistakes to be erased, but doorways into a deeper reality, quietly waiting to be confirmed. The discovery of the positron. In the early 1930s, a young physicist at the California Institute of Technology named Carl Anderson was not searching for antimatter. He had likely never even heard of Dirac's strange, mirrored solution at the time. He was simply studying cosmic rays, the constant, invisible rain of high-energy particles falling onto the Earth from deep space, hoping to better understand ordinary matter, not to discover its hidden twin. His tool was a device called a cloud chamber, a sealed container filled with vapor, cooled to the precise point where any charged particle passing through it leaves behind a faint, visible trail, like the white streak of a jet crossing a clear sky. Anderson placed a strong magnet around his chamber, knowing that a magnetic field bends the path of charged particles, curving negative particles one direction and positive particles the other. By measuring the curve, he could identify exactly what kind of particle had passed through. In 1932, while studying these cosmic ray tracks, Anderson found something that made no sense. A particle track curved exactly like an electron, the same mass, the same faint, delicate trail, except it bent in precisely the wrong direction. According to everything known about electrons at the time, this should have been impossible. A particle with the same mass as an electron, but a positive charge instead of a negative one, had no place in the universe as it was currently understood. At first, Anderson considered an electron simply traveling in an unexpected direction, but careful analysis of the track ruled that out entirely. What he had captured was something new, a particle nobody had ever directly observed before. Word eventually reached him that a strange, theoretical physicist named Dirac had already predicted such a particle should exist years earlier, hidden inside the second, discarded solution of his equation. Anderson named his discovery the positron, and almost overnight, Dirac's purely mathematical mirror image became an undeniable physical reality. This moment quietly changed what matter itself was allowed to mean. For the first time, scientists had proof that for every particle, there might exist a hidden, opposite twin, identical in mass, opposite in charge, capable of annihilating its counterpart back into pure energy the instant the two ever touched. Lying here now, far above your quiet, dark room, the same cosmic rays Anderson once studied are still falling, occasionally creating fleeting positrons that flicker into existence for only a fraction of a second. Brief flashes of antimatter, born and destroyed in the same fading heartbeat. A quiet reminder that the universe has always kept a mirror image of itself, hidden, just out of sight, waiting patiently to be noticed. Quantum tunneling. Imagine a ball rolling toward a hill. If the ball does not have enough energy, enough speed, enough force behind it, it will never make it to the other side. It will roll partway up the slope, lose all its momentum, and roll back down exactly the way it came. This is simple. This is obvious. This is how the entire visible world behaves every single time, without exception. Except, somehow, at the smallest scales of reality, it is not always true. Picture that same situation, but instead of a ball, imagine a single electron facing a barrier of energy it does not have enough strength to climb over. By every law of classical physics, it should be trapped, forever, on one side of that wall, with absolutely no way through. But because that electron does not exist as a single, solid point, because it exists instead as a smeared wave of possibility, something deeply strange becomes possible. Part of that wave does not stop at the wall. It does not climb over it. It simply continues, faintly, on the other side, as though the barrier were never fully solid to begin with. And every so often, the electron does not climb the hill at all. It simply appears on the far side, instantly, without ever having passed through the space in between, in any way you could meaningfully describe. Physicists call this quantum tunneling, and it is not a rare, exotic glitch confined to laboratories. It is happening constantly, silently, all around you right now. It is the reason the sun burns at all. Deep inside its core, hydrogen nuclei should not have enough energy to fuse together, not according to the old classical rules. They tunnel through the barrier that should stop them, fusing together anyway, releasing the very warmth and light that reaches your skin every single day of your life. There is something almost dizzying in sitting with this. A wall that should be absolute, impassable, total, is not actually total at all. It is more like a fog, thinner in some places than others, allowing the smallest pieces of the universe to slip through gaps that, by every rule of common sense, should not exist. Lying here now, in the quiet dark, somewhere inside your own body, and far above you, inside the heart of every star, the universe is constantly cheating its own laws, letting particles pass silently through walls that were never as solid as they appeared. Nothing was broken to make this happen. Nothing was forced. The wall was simply never as absolute as it looked, and the universe, given enough chances, will always find the thinnest place to slip quietly through. Hugh Everett and the Many Worlds Interpretation. In the mid-1950s, a young, soft-spoken graduate student at Princeton named Hugh Everett found himself deeply unsatisfied with something almost everyone else in physics had quietly learned to accept. The Copenhagen interpretation demanded a strange, unexplained event called collapse, a wave of possibility spreading smoothly through space, suddenly and violently snapping down into one single, random outcome, the instant anyone measured it. Bohr and Heisenberg never explained how this collapse physically happened, or what truly caused it. They simply insisted it occurred, as an unquestionable fact of nature. Everett refused to accept an unexplained miracle sitting at the very center of physics. So in 1957, Everett proposed something almost too strange to say out loud. What if collapse never actually happens? What if the wave function never snaps down into a single outcome at all? What if, instead, every single possible outcome simply continues to exist, fully and completely real, each one quietly splitting off into its own separate, parallel reality, the instant a measurement occurs? Under this idea, Schrödinger's cat is never truly both alive and dead inside one blurred, uncertain box. Instead, the universe itself splits into two complete, separate copies the instant the box is opened. In one entire branch of reality, the cat is alive, and an entire version of you walks away relieved. In another, equally real branch, the cat is dead, and another entire version of you grieves quietly beside the box. Neither version is more real than the other. Neither one is a ghost or a simulation. Both timelines simply continue, forever separated, never touching again, each one completely convinced it is the only reality that exists. Everett's own advisor found the idea so unsettling that he pushed Everett to soften his language before publishing it. Few physicists took it seriously at first. Everett, discouraged, eventually left academic physics altogether, working instead in defense analysis, his strange theory mostly forgotten for nearly 2 decades, until a small group of physicists rediscovered it and gave it the name that endures today: the many worlds interpretation. Lying here now, in this one version of the room you believe you are in, somewhere outside of anything you could ever observe or return to, countless other versions of you may be lying in countless other rooms, each one having made a slightly different decision, witnessed a slightly different outcome, living an entire separate life that branched away from yours in some quiet, forgotten moment you never even noticed passing. No one has ever found a way to test whether these other worlds are truly out there, or whether they are simply a beautiful, haunting piece of mathematics with nowhere real to live. Everett died in 1982, still convinced his branching worlds were real, never knowing whether history would remember him as a genius or simply as a man who saw too far into an idea no one else was ready to believe. The multiverse theory nobody believed. After Everett published his strange branching theory in 1957, almost nobody in physics paid any real attention to it at all. It did not get torn apart in furious debate, the way Einstein had once challenged Bohr across the Solvay conferences. It simply got ignored, quietly set aside, treated less like a serious threat to existing physics, and more like an oddity, too strange to bother arguing with. Niels Bohr himself, by then the most respected elder figure in quantum theory, reportedly dismissed the idea outright, unwilling to even seriously engage with it. The Copenhagen interpretation had already become the comfortable, accepted answer, taught in universities, repeated in textbooks, treated as settled fact, even though it still relied on an unexplained collapse nobody could fully justify. Everett's idea asked an entire generation of physicists to throw away that comfortable answer and accept instead that reality was constantly splitting into countless invisible branches nobody could ever see, measure, or return to. Almost no one wanted to follow him there. Everett left Princeton disheartened and largely walked away from academic physics altogether. He spent the following decades working for the Pentagon and private research companies, applying mathematics to nuclear war strategy and operations research, far away from the quiet, theoretical question that had once consumed him. Colleagues who knew him during these years often had no idea he had once proposed one of the strangest ideas in the history of physics. He rarely brought it up himself. For nearly 20 years, his branching universes sat almost entirely forgotten, buried inside an obscure doctoral thesis, gathering quiet dust in academic archives. It was not until the 1970s, when a small number of physicists began seriously re-examining the foundations of quantum mechanics, that Everett's idea was finally rediscovered, dusted off, and given the name history remembers it by today: the many worlds interpretation. By the time recognition finally began to arrive, Everett himself had grown weary and disillusioned, reportedly struggling with personal demons that shadowed his later life. He died suddenly in 1982, at only 51 years old, before he ever saw his idea grow into one of the most seriously debated interpretations in modern physics. Lying here now, in the quiet dark, somewhere in this same strange universe, an idea once dismissed as too bizarre to take seriously is now treated as one of the leading candidates for the deepest nature of reality itself, a quiet reminder that being ignored and being wrong are sometimes two entirely different things. John Bell and Bell's theorem. For nearly 3 decades after Einstein first proposed his EPR paradox, his challenge to quantum mechanics sat unresolved, treated by many physicists as more of a philosophical curiosity than a real scientific question. Whether those distant, entangled particles carried hidden, secret instructions exactly as Einstein believed, or whether something stranger and more connected was truly happening, seemed like a question that could never actually be tested. It felt, to most working physicists, like a debate with no possible experiment behind it, the kind of question you argue about late at night, but never actually settle. In 1964, a quiet Irish physicist named John Bell proved that assumption wrong. Working largely alone, almost as a side project away from his regular job at CERN, Bell found a way to turn Einstein's philosophical objection into something that could actually be measured in a laboratory. He imagined the entangled particles Einstein had described, carrying Einstein's hidden, secret instructions, fixed in place since the moment they were created. Then he worked out, mathematically, exactly how correlated these particles could possibly be if Einstein's hidden instructions were true, and nothing stranger was happening underneath. What Bell discovered became known as Bell's theorem, and it drew a hard mathematical line in the sand. If Einstein was right, if hidden variables truly existed, then the correlations between entangled particles could never exceed a certain fixed limit, no matter how the experiment was arranged. But if quantum mechanics was correct instead, if there were no hidden instructions at all, only the strange, instantaneous connection Einstein had mockingly called spooky action, then the correlations could rise higher than that limit allowed. For the first time, 2 completely different pictures of reality produced 2 different, testable numbers. Reality could finally be asked to declare a side. Bell himself was not entirely comfortable with where his own mathematics seemed to be pointing. He had quietly hoped, in some private corner of his thinking, that Einstein's vision of a calm, orderly universe might still turn out to be correct. He had built a test, not yet knowing which side it would ultimately favor. Lying here now, in this quiet, dark room, somewhere a single mathematical proof, written by one careful man working largely alone, had finally given the universe no place left to hide. After decades of argument, of dice and spooky action, and sealed envelopes never opened, Bell had built the lock. All that remained was for someone, somewhere, to finally turn the key. Quantum entanglement. Picture 2 particles, born together in a single shared event. An instant of creation that binds them in a way nothing afterward can ever fully undo. The moment they form, their properties become linked, not loosely, not approximately, but completely, woven into a single shared mathematical description, even as the particles themselves begin drifting apart, farther and farther, eventually separated by entire continents, or by the cold emptiness between stars. This is entanglement, and it is not simply a strange correlation, the way 2 coins might happen to land on matching faces by pure chance. A coin flip, however surprising, was always going to land on whatever side it landed on, the moment it left your hand. Entangled particles are different. Before either one is measured, neither particle has a definite property at all. Not a hidden one, not a secret one. None. They exist only as a single, shared wave of possibility, spread across both particles simultaneously, no matter the distance separating them. Then, the instant one particle is measured, forced to reveal a definite state, the other particle, even an entire universe away, instantly settles into a matching, correlated state as well, not a fraction of a second later, not delayed by the time it would take a signal to cross that distance, even traveling at the speed of light. Instantly. Following the path Bell had carefully drawn through the dark, physicists eventually built real experiments to test exactly this, sending entangled particles to distant detectors and measuring their correlations directly. Again and again, the results broke straight through the limit Bell's mathematics had set for any theory built on hidden, secret instructions. Einstein's sealed envelopes were never opened, because they had never existed at all. This does not mean information is secretly traveling faster than light, slipping past Einstein's relativity through some hidden back door. Nothing useful can be sent this way. No message, no signal, no warning. And yet the correlation itself, the strange, perfect agreement between two distant particles, remains undeniably, instantaneously real, with no story of cause and effect that travels through space to explain it. Lying here now, somewhere on this planet, entangled particles are sitting quietly in laboratories, linked across distances that should make any ordinary communication impossible, holding a connection that does not travel, does not delay, and does not weaken with distance. The universe is not simply vast and empty. It is, in certain hidden corners, quietly stitched together by threads that ignore distance entirely, refusing, for reasons no one has ever fully explained, to ever let go of each other completely. The measurement problem. By now, you have heard the same strange word again and again, drifting quietly underneath almost every chapter of this story. Measurement. A particle exists as a blurred wave of possibility until measurement forces it to choose. A cat is both alive and dead until measurement opens the box. Two entangled particles share a single fate until measurement collapses it into one definite outcome. The word does an enormous amount of quiet work in this story, and yet even now, nobody has ever fully explained what measurement actually is. This is called the measurement problem, and it might be the deepest, most uncomfortable question quantum mechanics has never managed to answer. What precisely counts as a measurement? Does it require a conscious mind, a human being, deliberately looking? Or does it simply require any interaction at all, an atom bumping into another atom, with no consciousness involved whatsoever? If a single photon strikes a detector deep inside a machine, with no human anywhere nearby to look at the result, has a measurement already happened? Or does the wave function continue spreading, blurred and undecided, until a person finally checks the readout? Nobody has ever drawn a clean, universally agreed line between the quiet, blurred quantum world and the solid, definite world you experience while lying here right now. Bohr simply insisted that somewhere a line exists, without ever specifying exactly where. Everett's many worlds idea tried to erase the line entirely, insisting collapse never truly happens at all, only endless, silent branching. Other physicists have proposed it happens automatically, The instant a quantum system grows large enough, complicated enough, tangled enough with its surroundings, though no one fully agrees on exactly when that threshold is crossed. What makes this question so unsettling is how close it sits to your own existence. You are made of atoms. Atoms that, individually, behave exactly like the strange, blurred particles in every story you've heard tonight. And yet you do not feel blurred. You do not feel like a fog of overlapping possibilities, lying uncertainly in several places at once. Something, somewhere, between the smallest building blocks of your body and the solid, singular person reading, listening, drifting towards sleep right now, makes the blur disappear. Nobody has ever found that exact boundary. Lying here now, in this quiet, dark room, you exist as one single definite person, and the question of precisely where and precisely how that certainty was finally created out of so much underlying fog remains one of the oldest, most unresolved, haunting mysteries physics has never managed to close. The observer effect. The double-slit experiment first revealed it, quietly, almost as an afterthought, buried inside a strange pattern of stripes on a screen. The moment a detector was placed near the slits, just to watch which path the electron actually took, the interference pattern vanished completely. The electron stopped behaving like a spread-out wave and started behaving like an ordinary, solid little particle, choosing one slit and only one. This single, simple result has haunted physics for over a century, and it is known simply as the observer effect. It is important to sit, for a moment, with what this does not mean, because the popular version of this idea has drifted far from what physicists actually discovered. This is not proof that human consciousness, your mind, your attention, your awareness, possesses some mystical power to shape reality through sheer thought alone. That version of the story, however tempting, however often repeated, is not what the experiment shows. What collapses the wave is not a person's gaze. It is interaction. The detector itself, a cold, mechanical, unconscious piece of equipment, physically interacts with the electron in order to record which path it took. That interaction alone is enough to destroy the delicate wave pattern, whether or not a human eye ever looks at the result afterward. But this distinction does not make the mystery disappear. It only relocates it. Because now the haunting question becomes, what exactly counts as an interaction strong enough to collapse the wave? Why does bouncing off a single, simple detector force the electron to choose, while drifting silently through empty space does not? Where, precisely, is the line between gently brushing against the world and being forced to reveal a definite, solid answer? This is why physicists today speak less about observers and more about decoherence, the slow, quiet process by which a fragile quantum system becomes entangled with its surroundings, spreading its delicate uncertainty outward into the environment until the original blur becomes practically impossible to detect again. Not erased, just scattered too widely, too messily, to ever be gathered back into a single, clean wave. Lying here now, your own body is constantly interacting with the air around you, with light, with the surface beneath you, collapsing countless tiny quantum possibilities every fraction of every second, not because anyone is watching, but because the universe itself cannot stop quietly touching everything within it, and every touch, however small, asks reality to make up its mind. Richard Feynman and the Path Integral. In the 1940s, a brilliant, restless young physicist named Richard Feynman looked at the strange behavior of particles and decided to ask a question nobody else had quite asked in this particular way. Heisenberg had built a mathematics of sudden jumps. Schrödinger had built a mathematics of smooth, flowing waves. Both worked. Both gave the same answers, despite looking nothing alike. Feynman wanted to know if there was a third way to picture the same hidden truth, something even stranger, something that might finally explain why quantum mechanics behaved the way it did. What he proposed sounds almost too absurd to take seriously, and yet it works perfectly. Feynman suggested that when a single particle travels from one point to another, it does not simply take the one path you might expect, the shortest, the smoothest, the most obvious. Instead, that particle somehow takes every single possible path simultaneously, not metaphorically, not as a strange mathematical trick layered on top of a simpler truth underneath. Every path, all at once, the straight line between 2 points, a wide, looping curve far out into space, a jagged, impossible zigzag bouncing wildly in every direction. Every single one of these paths, infinite in number, contributes something to the particle's final observed behavior. Feynman showed that you could calculate the probability of a particle ending up in any particular place by adding together a tiny contribution from every single one of these infinite, possible paths. Most of these paths cancel each other out, interfering destructively, the same way overlapping ripples on a pond can flatten into stillness. Only the paths clustered closely around the one smooth classical path you would normally expect reinforce each other strongly enough to survive. This is why, in the world of everyday visible objects, only one path ever seems to matter. It is not that the others do not exist. It is that they quietly cancel themselves into invisibility, leaving only the familiar, sensible one behind. This new approach, called the path integral, gave physicists an entirely new way to calculate the strange behavior of particles, and it matched Heisenberg's grids and Schrödinger's waves perfectly, proving once again that the same deep truth could be reached by 3 wildly different roads. Lying here now, in the stillness of this room, every photon of light reaching your eyes, every electron moving quietly through your body, is not simply taking one clean, obvious path through space. In some deep mathematical sense, it is exploring every conceivable path at once, an infinite, invisible fan of possibilities, quietly collapsing down into the one smooth story your senses are allowed to witness. Quantum electrodynamics. Out of Feynman's strange path integral, alongside the parallel work of 2 other physicists, Julian Schwinger in America and Shinichiro Tomonaga in Japan, working independently and arriving at the same hidden truth from completely different directions, came a theory that would describe the interaction between light and matter with a precision that still feels almost unbelievable today. They called it quantum electrodynamics, and it remains, even now, one of the most accurately tested theories ever created by the human mind. The theory describes something deceptively simple on its surface: how light and matter talk to each other. Every time an electron absorbs or releases a photon, every time 2 charged particles push or pull against one another, quantum electrodynamics describes exactly what happens, using Feynman's strange picture of countless overlapping paths, added together, mostly cancelling, leaving behind only the precise, observable outcome. Feynman developed a simple way to visualize these interactions, little sketches showing particles meeting, exchanging photons, and separating again, now known as Feynman diagrams, simple enough to draw on a napkin, yet capable of representing calculations of staggering complexity underneath. What makes this theory so remarkable is not just its strangeness, but its accuracy. Quantum electrodynamics allows physicists to calculate certain properties of the electron to more than 10 decimal places, and when those predictions are tested against real experiments, they match, not approximately, not closely, to a precision so exact that it is often compared to predicting the distance between two cities accurately enough to account for the width of a single human hair. No theory in the history of science has ever been confirmed with this level of precision. And yet, underneath this staggering accuracy, the theory still depends entirely on the same strange, unresolved foundation as everything that came before it. Particles still exist as overlapping waves of possibility. Outcomes are still fundamentally probabilistic, governed by chance rather than certainty. Quantum electrodynamics did not resolve any of the deep philosophical unease that had haunted physics since Planck's first reluctant quantum. It simply proved, with overwhelming precision, that the strangeness was not a mistake. Lying here now, every flicker of light reaching your eyes, every faint warmth touching your skin, is being governed by a theory so precise it can predict outcomes with a level of certainty most sciences could only dream of, built entirely on top of a foundation that remains, after a century of staggering success, every bit as strange and unresolved as the day Planck first stumbled upon it. David Bohm and the pilot wave. While most physicists by the 1950s had quietly settled into accepting the Copenhagen interpretation, with its unexplained collapse and its refusal to ask what lies beneath the blur, one physicist refused to let the question go. His name was David Bohm, an American physicist who, by the time he developed his ideas, had already been forced out of his university position and out of the country itself, accused during the paranoia of the 1950s of having communist sympathies, eventually finding refuge teaching physics far from home, in Brazil and later in England. Bohm could not accept Bohr's quiet insistence that asking what happens beneath the wave function was a meaningless question. He believed there must be a deeper layer of reality, something concrete, something definite, hiding underneath the fog that Copenhagen refused to examine. In 1952, he built an alternative, one that Einstein had quietly hoped might someday exist, a theory where particles do, in fact, have real definite positions at all times, never blurred, never smeared into probability. In Bohm's picture, every particle is a genuine, solid little object, guided invisibly through space by something he called a pilot wave, a real physical wave spreading through the universe, silently steering each particle along a hidden, precise path. The particle was never actually uncertain. It only appeared uncertain to us, because we could never fully see or measure the guiding wave moving quietly underneath it. Remarkably, Bohm's strange picture predicted the exact same observable results as ordinary quantum mechanics, the same statistics, the same double-slit pattern, the same entangled correlations, despite being built on an entirely different, deterministic foundation underneath. There was a price hidden inside Bohm's elegant solution, one that troubled even those who admired it. His pilot wave had to act instantly across the entire universe at once, guiding distant particles in perfect, immediate coordination, no matter how far apart they were. He had restored definite reality to the particle, but only by accepting an even deeper, stranger kind of universal connection than Copenhagen had ever required. For decades, Bohm's theory was largely ignored, overshadowed by Copenhagen's dominance and clouded by his political exile. Few physicists seriously engaged with it, even though it could never be proven wrong using ordinary experiments, since its predictions never differed from standard quantum mechanics. lying here now in this quiet, dark room, somewhere underneath the blurred, uncertain world you have been told is fundamentally unknowable, a quiet, unproven possibility still lingers that every particle in your body has always known exactly where it is, silently guided by a hidden wave, too vast, too invisible, and too deeply woven into the universe for anyone to ever fully see. Wheeler's delayed choice experiment. In the 1970s, the physicist John Wheeler, a man who had once worked alongside Bohr himself and helped carry quantum theory into the modern age, proposed a thought experiment so unsettling that it seemed to threaten something far more sacred than uncertainty alone. It seemed to threaten the past itself. Return once more to the double-slit experiment, the same two narrow openings that had haunted this story from the very beginning. A single particle approaches the slits. According to everything already explored tonight, the particle decides, in some deep, unresolved way, whether to pass through as a spread-out wave, slipping through both slits and interfering with itself, or whether to pass through as a single, definite particle, choosing only one. The detector you place near the slits, watching or not watching, seems to determine which behavior occurs. Wheeler asked a question that sounds, at first, almost too simple. What if you wait? What if you delay your decision to watch, choosing whether or not to measure the particle's path only after it has already passed through the slits, after it has already, in some sense, made its choice? According to the strange mathematics of quantum mechanics, it does not matter. Even if you make your decision to observe at the very last possible instant, long after the particle has already passed through the slits, your choice still determines, retroactively, whether the particle behaved as a wave or as a single, solid object the entire time. Choose to watch, and looking backward, the particle had always traveled through only one slit. Choose not to watch, and looking backward, it had always existed as a spread-out wave, passing through both. The decision made now appears to reach backward and decide what already happened. Physicists have actually built and tested versions of this experiment, using clever arrangements of mirrors and detectors to delay the choice as long as physically possible. Every single time, the results confirm Wheeler's unsettling prediction. The past, in some deep sense, refuses to be fixed until the story of its own measurement is finally completed. Wheeler did not believe this meant time travel was real, or that anyone could reach backward and rewrite history in any way that could be used or controlled. He believed something stranger and quieter than that the universe itself may not write its own story in a fixed, permanent order. That the past, in some small, careful sense, remains unfinished, waiting patiently for its own ending before it is finally allowed to become true. Lying here now, in the dark, somewhere in your own past, in moments you believe are already finished, already sealed, already unchangeable, the universe may still be quietly waiting, holding its breath, for some small, distant measurement still left to come. Quantum decoherence. By the time the measurement problem and the observer effect had haunted physics for decades, with no agreed answer for what truly counts as a measurement, a quieter, more modern explanation began to emerge, one that did not require collapse, did not require consciousness, and did not require splitting into endless hidden worlds. It simply asked a different question. What actually happens, physically, when a fragile quantum system meets the busy, crowded, ordinary world around it? A single particle alone, isolated from everything else, can sit quietly in a delicate state of overlapping possibilities for a long time, its wave of potential undisturbed, clean, and whole. But nothing in the real universe stays truly isolated for long. The moment that particle begins interacting with its surroundings, with stray photons of light, with the air around it, with the countless other particles constantly bumping and brushing against everything else in existence, something quiet and irreversible begins to happen. The particle's delicate uncertainty does not vanish. It spreads. It leaks outward, entangling itself with everything nearby, smearing its fragile blur across an enormous, complicated web of surrounding particles, until the original, clean overlap becomes hopelessly scattered, hidden inside a tangle far too vast and messy to ever gather back together again. This is called decoherence, and it offers something quietly different from collapse. The strange quantum overlap is never truly destroyed. It does not vanish in some sudden, mysterious instant the way Copenhagen once demanded. It simply becomes diluted beyond recognition, scattered so widely across the environment that recovering it again would be like trying to gather a drop of dye back out of an ocean it has already dissolved into. From the outside, it looks exactly like collapse. From the inside, mathematically, the strangeness is still technically there, only buried too deep to ever find again. This is why you, made of trillions upon trillions of particles, constantly touching, bumping, and interacting with the world around you, never personally feel like a blurred cloud of possibilities. Decoherence happens to you almost instantly, in fractions of a fraction of a second, the moment any of your particles brush against anything else nearby. The quantum world is not separate from your world. It is simply drowned, almost immediately, in the overwhelming noise of everything touching everything else, all the time. Lying here now, in this quiet, dark room, every part of you is constantly, silently decohering, your own trillion delicate uncertainties scattering outward into the surrounding air the instant they form, leaving behind only the one solid, singular version of you that you have been allowed to ever feel. The birth of quantum field theory. By the middle of the 20th century, physicists faced a quiet but uncomfortable contradiction sitting underneath everything they had built so far. Quantum mechanics had successfully described particles, atoms, and the strange blur of possibility surrounding them. But it had been built largely without fully respecting Einstein's relativity, the deep law insisting that nothing in the universe should be fixed in number, fixed in identity, or capable of moving faster than light. And yet, in laboratories around the world, something deeply strange kept happening. Particles were being created and destroyed, appearing out of empty space, vanishing into nothing, as though the universe itself refused to keep a fixed inventory of what existed. This led physicists toward a deeper, stranger picture of reality, one that did not start with particles at all. Instead, it proposed that the most basic layer of the universe is not made of tiny solid objects, but of fields, invisible, continuous structures stretching across the entirety of space, vibrating quietly everywhere, even in what appears to be completely empty space. Under this view, what we call a particle is not a fundamental thing in itself. It is simply a small, concentrated vibration, a ripple rising briefly out of its underlying field, the way a single wave rises briefly out of an ocean before settling back down into stillness. An electron, under this picture, is not a tiny ball traveling through empty space. It is a tiny excitation, a brief, localized disturbance rising out of something physicists call the electron field, a field that fills the entirety of space itself, everywhere, invisibly, whether or not any electron happens to be rippling out of it at any given moment. A photon is the same kind of ripple, rising instead out of the electromagnetic field. Every kind of particle in the universe under this framework is simply a different kind of field, each one stretching silently across all of existence, waiting to ripple. This explained, almost effortlessly, the mystery that had quietly bothered physicists for years. Particles could appear and disappear because they were never truly solid objects to begin with. They were only ever temporary ripples, rising and falling out of fields that never go away, fields that were always there, underneath everything, even in the stillness of empty space. Lying here now, in the quiet dark of this room, you are not surrounded by empty space at all. You are resting inside an ocean of invisible fields, stretching infinitely outward in every direction, fields that fill this entire room, this entire planet, this entire universe, silently capable, at any moment, of rippling into existence the very particles that make up the breath moving quietly in and out of your chest. The Standard Model. By the second half of the 20th century, physicists had discovered far more particles than anyone originally expected. What began with a simple picture of electrons, protons, and neutrons had grown into a strange, sprawling family of previously unknown particles, appearing unexpectedly out of high-energy collisions, each one seemingly unrelated to the last. For a while, this collection felt closer to a chaotic zoo than a clean, organized theory. Physicists wanted to know if there was a hidden order holding this entire collection together, a single underlying blueprint quietly governing everything that exists. Slowly, piece by piece, through decades of careful theoretical work and painstaking experimentation, that blueprint finally emerged. It came to be called the Standard Model, and it remains even today the most complete and successful description of matter and force that physics has ever produced. It organizes everything you have heard about tonight, and everything you have never directly heard about, into one single elegant structure. At its foundation are two basic kinds of particles: fermions, the building blocks of matter, things like electrons and quarks, the tiny particles that combine in specific groups of three to form every proton and neutron inside every atom in your body, and bosons, the particles responsible for carrying force, allowing other particles to interact, push, pull, and influence each other across the universe. Photons, the particles of light, carry the electromagnetic force. Other bosons carry the strong force, binding quarks tightly together inside every atomic nucleus, and the weak force responsible for certain kinds of radioactive decay, the same quiet process that once made Schrödinger's cat such an unbearable mystery. The Standard Model does not explain everything. It says almost nothing about gravity. It does not explain dark matter or dark energy. Two mysterious quantities astronomers know must exist, simply by observing how galaxies move, yet have never directly detected or understood. Even now, it remains an incomplete map, astonishingly accurate within its borders, yet surrounded by vast, unexplained territory just beyond its edges. Lying here now, in the quiet dark of this room, every single atom inside your body is built from this same handful of fundamental particles, governed by this same elegant blueprint, a blueprint physicists spent the entire 20th century slowly assembling, piece by piece, out of an unruly zoo of particles that, for a brief, confusing moment, seemed like they might never make sense at all. The Higgs boson for decades, one quiet, nagging question sat unresolved at the heart of the Standard Model. The equations worked beautifully, describing particles and forces with remarkable precision, but they carried a strange, embarrassing flaw. By the math alone, every particle in the universe should be massless, traveling eternally at the speed of light, the same way a photon does, with nothing ever slowing down enough to form an atom, a star, or a single solid object of any kind. And yet here you are, lying in a body that clearly, undeniably, has weight and substance. Something was missing from the blueprint. In 1964, a small group of physicists, including a quiet Scottish theorist named Peter Higgs, proposed a strange solution. What if empty space itself was not truly empty? What if the entire universe was secretly filled with an invisible field, stretching everywhere, through every star, every atom, every quiet, dark room, a field that nothing could fully escape? Particles moving through ordinary empty space would glide freely, unaffected, exactly as the equations demanded. But particles moving through this strange, invisible field would feel a kind of drag, a resistance, as though wading through something far thicker than empty space should ever allow. That resistance, that invisible drag, is what we experience as mass. This invisible field came to be called the Higgs field, and like every other field in quantum theory, it predicted that a disturbance rippling through it should appear as a genuine, detectable particle, a single, fleeting ripple, briefly rising up out of the field itself. They called this predicted ripple the Higgs boson, and for nearly 50 years it remained nothing more than a theoretical prediction, hidden somewhere beyond the reach of any machine ever built. Then, in 2012, deep underground in Switzerland, inside the enormous particle accelerator known as the Large Hadron Collider, scientists finally smashed protons together with enough violent energy to briefly summon that ripple into existence. For a fraction of an unimaginably small fraction of a second, the Higgs boson flickered into reality, confirming, after nearly 5 decades of uncertainty, that the invisible field Higgs had proposed was real all along. Lying here now, in this quiet, dark room, the only reason your body has weight at all, the only reason matter does not simply dissolve into a meaningless blur of massless light, is that you are resting inside an invisible field stretching across the entire universe, an unseen, silent presence that has been quietly giving substance to existence since the very first fraction of a second after the universe itself began. The rise of quantum computing. For nearly a century, the strangeness of quantum mechanics had mostly remained locked inside the careful, controlled silence of laboratories, studied for its mysteries rather than its usefulness. But by the 1980s and 90s, a small group of physicists, including Richard Feynman himself, began asking a different kind of question. If the universe computes its own behavior using superposition, entanglement, and probability, why couldn't we build machines that compute the exact same way? An ordinary computer, the one you might be holding right now, thinks in absolute certainties. Every single bit of information is either a 0 or a 1, fully one or the other, never both, never blurred. A quantum computer breaks this rule entirely. Instead of ordinary bits, it uses something called qubits, tiny quantum systems that, like Schrödinger's cat sealed inside its box, can exist in a blurred combination of 0 and 1 simultaneously, a genuine, unresolved overlap of both possibilities at once, right up until the very moment they are measured. This is not simply a faster way of counting. With enough qubits entangled together in just the right way, a quantum computer can explore an almost unimaginable number of possibilities all at once, the same strange, overlapping multitude of paths that Feynman once described particles taking through space. For certain very specific problems, ones involving searching through enormous numbers of possibilities, or simulating the chaotic, tangled behavior of other quantum systems, this allows a quantum computer to find answers that would take an ordinary computer an unreasonable amount of time, sometimes longer than the current age of the universe itself, to ever calculate. There is a strange, quiet irony hidden underneath this entire pursuit. Decoherence, the same quiet process that explains why your own body never feels like a blurred cloud of possibilities, is the single greatest enemy quantum computers must constantly fight against. The moment a fragile qubit brushes too closely against heat, vibration, or stray light from its surroundings, its delicate quantum blur collapses, and the advantage it offered disappears completely. Building a quantum computer means building a tiny, perfectly isolated pocket of the universe, one carefully shielded from the same constant, unavoidable noise, decohering everything around you, right now, in this very room. Lying here now, somewhere in laboratories scattered across the world, machines cooled down to temperatures colder than deep space are carefully holding fragile qubits suspended in uncertainty, racing quietly against the same relentless decoherence that has been silently shaping reality since the very first moment Planck stumbled upon his uncomfortable, reluctant staircase of energy, nearly 125 years ago. Quantum biology. For most of the 20th century, quantum mechanics and biology lived in two completely separate worlds. Quantum strangeness belonged to the cold, controlled silence of particle laboratories, locked away from anything as warm, wet, and chaotic as a living cell. Decoherence, the same relentless process keeping your own body solid and definite, was assumed to happen instantly, violently, the moment any delicate quantum effect tried to survive inside the messy, crowded interior of a living organism. Life, scientists believed, was simply too warm, too wet, too noisy a place for anything as fragile as superposition or entanglement to ever survive. Then researchers began noticing strange, unexplained efficiencies hiding quietly inside ordinary biological processes, things that did not seem to make sense using classical physics alone. Inside the leaves of plants, during photosynthesis, a single packet of light energy needs to travel from where it is captured to a specific location deep within the cell, where it can finally be converted into usable energy. Classically, this energy should wander randomly, bumping inefficiently from one molecule to another, losing precious energy along the way, the same way a ball might lose momentum to bouncing randomly. Instead, researchers found the energy moving with startling, almost impossible efficiency, as though it were quietly testing multiple paths at once. The same strange behavior Feynman once described, particles exploring through empty space before settling into the most efficient route available. Stranger still, certain birds, including the European robin, appear capable of sensing the Earth's magnetic field well enough to navigate vast distances during migration, using a process some scientists believe depends on a delicate, fragile quantum effect occurring inside specialized molecules in their eyes, a subtle entanglement between electrons that should, by every ordinary expectation, collapse instantly inside something as warm and chaotic as a living bird, and yet somehow it appears to survive just long enough to do its quiet, essential work. None of this is fully settled. Quantum biology remains a young, deeply contested field, with many scientists still skeptical that true quantum effects survive meaningfully inside such warm, noisy, biological environments, rather than disappearing into ordinary classical explanations after all. But sit with the possibility for a moment, lying here now, in this quiet, dark room. Somewhere inside your own body, in this exact moment, the same strange quantum rules that govern electrons jumping between energy levels, the same fragile entanglement that haunted Einstein for the rest of his life, may be quietly, invisibly at work, helping a tiny bird somewhere on the other side of the planet find its way home, using a piece of the deepest, strangest physics ever discovered, hidden silently inside something as warm and fragile as life itself. The search for quantum gravity. This is the final piece of the story, and it remains, even now, unfinished. Quantum mechanics describes the smallest things in the universe with staggering precision: electrons, photons, fields rippling through empty space. General relativity describes the largest things in the universe with equal precision: planets, stars, the slow, graceful curve of space and time itself, bending under enormous gravity. Each theory, on its own, is one of the most successful achievements in the history of human thought. And yet, whenever physicists try to combine them, to describe both at once, the math collapses into nonsense. The problem becomes unavoidable in only a few extreme places in the universe: the exact center of a black hole, where an enormous mass is compressed into an infinitely small point, or the first unimaginably brief fraction of a second after the universe itself began, when everything that exists was compressed into a space far smaller than a single atom. In these places, gravity becomes so strong, and space becomes so small, that both quantum mechanics and general relativity should apply at the exact same time. But nobody has ever found a way to make them agree. Physicists have spent decades searching for a theory of quantum gravity, one final framework that could finally unite the smallest and largest scales of existence into a single, coherent story. Some have proposed string theory, suggesting that every particle is not truly a point, but a tiny, vibrating string, far too small to ever directly observe. Others have proposed loop quantum gravity, suggesting that space and time themselves are not smooth and continuous, but built from tiny, discrete loops, a kind of final, deepest staircase hidden beneath everything else. Neither theory has ever been confirmed. Neither has ever made a prediction that current technology could actually test. This is where the story you have been falling asleep to finally runs out of certainty. After more than 100 years, after Planck's reluctant staircase, after Einstein's stubborn dice, after Bohr's quiet insistence, after Bell's careful proof, after Higgs's invisible field, physics still does not know how space, time, and gravity ultimately fit together with the strange, blurred world hiding underneath everything you have. Tonight, finally learned to call reality. Lying here now, in this quiet, dark room, you are resting inside a universe that, even after a century of staggering discovery, still does not fully understand itself. A quiet, unfinished mystery, stretching from the smallest flicker of a particle to the vast, silent curve of space and time itself, waiting patiently, perhaps for centuries more, for someone to finally find the way the smallest and largest pieces of existence were always meant to fit together.